Okay, so this is the part one anyway, the tutorial for Project 1. There will be another part where I do some kind of chalkboard style, probably on the iPad. It's a little harder to do that on the computer, but this I'm going to walk through at least the project document, and then I'll probably jump over logically for a little bit too, and we'll talk about some things over there about how you're actually going to build this thing. So Project 1 really brings together everything we've done in the labs in the last 3 weeks. So every single component you built, I think without exception, is going to be involved in this project, which is why we built them all. So if you didn't finish the labs or you built them and they didn't work, fix them because they need to work. They have to be completely assembled and operating in order for your project to work. And the grade value adds up, right? So those labs are worth like 2% each. This project is 15% total. So if you don't fix those things and your project doesn't work, your marks are going to suffer pretty terribly when this doesn't operate. So get those things fixed, get them operational, so that you can actually complete the project successfully. So there's two parts to this project. The first part, and I'll come back to these basic instructions in a sec. The first part is you're actually going to build a microprocessor. So all the things you constructed, the ALU, the registers, the bus system, what else? Demultiplexers, the buses, all that stuff is going to be involved in the construction of a microprocessor in Logically. So you're going to simulate one. And this is going to be a fairly simplified version of a microprocessor compared to the one that we're going to use in the rest of the course, right? So if you already watched the lecture for this week, you'll know that the microprocessor we're going to use in the rest of the course is an Atmega 328. It has 128 possible instructions, lots of memory, it's really fast. The one that we're going to build, based on your ALU, has 8 functions, right? It can do 8 things versus a larger microprocessor that can do 128 things. So again, scaled down version of something like that. So the first thing you're going to do is build the microprocessor. The second thing you need to submit is a written portion, a report based on that microprocessor. So 2 sections. The build is worth the most, that's 10% right there, and then the report is worth a little less, 5%. And we'll walk through each of those in detail, but that's the 30,000 foot view, quick summary of the project. So start at the top now. Key instructions, submission requirements. You're going to submit 2 things. You're going to submit the Logically file through a Blackboard Dropbox, the same way you've been submitting assignments, or labs rather, so far. So it's just going to be a drop. You're going to fire your Logically file in there, and I'll be able to get it that way. The second thing you're going to submit through Turnitin, which is our plagiarism checker, is your report portion. So that should look like this. So Logically file through the Dropbox, and then separately through the Turnitin Dropbox, you're going to submit your report. So that's the first 2 things. The third key instruction, same as the labs, is every single IC involved in your project has to have your initials in it. So either in like the file name off on the side, that's fine, or on the actual IC is preferable. But every single IC has to have your initials just to verify that it's yours for your entire build. And then, of course, like everything else, anyone who's found to have submitted someone else's work or a portion of someone else's work or committed plagiarism of any kind, academic misconduct of any kind, as specified in college policy, I will file for academic misconduct. No hesitation there from me. So then that's just kind of the submission instructions. Then we get into specific instructions. So what exactly are you building? So let's look at this. You are building a microprocessor. Your microprocessor has data inputs. So that looks a lot like Lab 3. And that's probably something worth saying at the beginning. Lab 3 is actually going to be the template for your project. So the very first thing we're going to do when we start the project, and I'm going to show you in a second, is open Lab 3 and start building from there. So Lab 3 had data inputs at the top. And then it had some code memory registers at the top. I think your lab had 2. And then you had a bus, right, which allowed you to send data from multiple locations down to 1 location. You had a single CPU register. In this project, we're going to have 2 CPU registers. Then what we're adding is an ALU. That's a big addition to Lab 3. So we built it in Lab 2, but we're going to add the ALU in here. Then we have some demultiplexers, which go out to DM registers. And again, in Lab 3, you had 2 of those. And this one is just going to get a little bit bigger. So the structure here is largely the same as Lab number 3. The biggest addition we've made is the ALU, and everything else is just going to get a little bit bigger. So let's go through. And I'll show you kind of how to build a lot of these things in a little bit, but this is a big list of requirements. I won't necessarily go through all of these. They're just meant to specify and give you a bit of a checklist of things that you need to include. But it specifies, okay, there's 4 data memory registers. Those are the ones down here. There's 4 code memory registers, so up here, right? See how it's getting bigger? In Lab 3 we had 2, now we have 4. There's 2 CPU registers instead of 1. Then we add in the ALU. Those are the key systems. We're also going to have a bus system, right? That sounds exactly like Lab 3. We have data inputs to the code memory registers. That's the same. Then I give you a list of control inputs. So you should have, at the end of your project, this many switches for controlling stuff. And then I've given you a list of design requirements. What are the things you need to do to actually make this kind of look functional and testable for me? Your wire paths need to be relatively traceable. Like, they don't need to be all separated, but they shouldn't be kind of spaghetti factory style. They should be a little bit organized. You want to group your types of lines together, so like in buses. So your data lines all go together, your address lines, your control lines go in groups. Follow the block diagram layout. So when your project is done, it should be ordered like this, top to bottom, just so I can follow it. And then some more things you can do that'll be helpful for you. So you know, we're going to use decoders. We already talked about those in Lab 3. We're going to use a demux to control a write signal. That again is from Lab 3. And one thing I'm going to get you to do is use a push button for the clock. It just makes it easier for your testing. It gives you the on-off, which is what you're always doing, rather than having a switch that you have to click twice. And then I also want you to include, and I'll show you this in Logically, comment blocks for specific things. One that has your name and student number, just to correlate all that together. And then I want you to include a bunch of truth tables for every control input. So again, I'll show you what that means in a little bit. But all your ALU functions I want a truth table for, and then your register selection I want truth tables for. And then lastly, labels on your inputs. So, you know, put a label over the clock that says it's the clock. Labels over your registers that just give them numbers, so maybe R1, R2, R3, R4, that sort of thing. And then labels over each component, so ALU, data bus, all that kind of stuff. Largely just so you, when you're troubleshooting this thing and building it, kind of can track what's going on, and so when I open up to review it, I can follow through in a way that's clear. So let's deal with this logically part first, and then no, let's talk about the report. Otherwise, I'm going to lose you. So let's talk about the report, and then we'll jump over to logically because then you'll start paying attention again. So let's go through the report. So 5% of the total 15, so 1/3 of the project is a report section. It's not that long. So title page, include that there. I want you to have then 4 additional sections. So the first section is I want you to pick 4 logic circuits from your project. So any 4, could be literally anything: multiplexer, bus, demultiplexer, ALU, register. You know, you take your pick. And I want you to give me a 100-word description of the design and operation of each of those. So that's 400 words right there. 100 words total per circuit. So 400 words total. Then I want you to give me a technical description of the complete operation of your microprocessor. So that doesn't mean like, you know, my microprocessor is a computer and it processes data. That's not technical. I know how this thing works, so I want you to give me a technical description. You know, data gets loaded in the form of binary into the code memory registers. Code memory only gets loaded when the write function is active and the clock pulses. Once it pulses, the registers are loaded. And then you get register into the CPU, and you do that by choosing the following. And give me a technical description of how it works in that kind of language. So that's the third part, and that's 300 words, not that long. The fourth part is to give me screenshots. This is more reflective of the labs we've been doing. And I want you to give me 2 sets of screenshots. One set, and again, we'll go through this in Logically in a sec, it'll make a little more sense. One set is just loading data in the code memory registers and storing a result from that data into a data memory register. So what that's saying is, load some data up here. This is exactly like Lab 3. Pass that data through and store it in the bottom. That's virtually Lab 3. We have the ALU in here, so it's going to do something to it, but same idea, top to bottom. Then, so that's part 1, give me screenshots, step by step, and description of that happening. And then what we're also going to be able to do in this one that's different than Lab 3 is we're going to be able to take the data in the data memory registers at the bottom and pass it back up around again. So that's the second set of screenshots, is you're going to take data from down here, pass it back around to the CPU, process it, and store it somewhere else. So that's the second set of screenshots, is reuse data and circle it back to the CPU. So 2 sets of screenshots with commentary giving me these these functions. The reason I need you to include these is one, so that I know that you know how to run your microprocessor. That's the biggest thing. So this is a really key requirement. Is like just building is not enough. You need to know how to use it, and that's what these are for. The other thing this is really, really important for is if you submit your microprocessor and I open it up and I can't figure it out or can't get it working, or it seems like something's kind of wrong, but then you've got screenshots that show that it's working. I'm going to email you and say, hey, like, can you just double check? Did you send me the right file? Is this the right microprocessor? It's not really behaving the way your screenshots show. We need to figure this out so I can mark it and give you the mark you deserve. So really important that you do that portion. Can't really mark the project or the report without that. That's a critical requirement. Then the last thing you're going to do is give me a single page data sheet. So you should know what a data sheet looks like, especially from your electronic fundamentals course probably, and maybe digital circuits too. You're probably looking up some of those for those ICs you're using. So check out just a generic data sheet to know what's even included in those things. And I want you to build me a one-page data sheet that includes the following things. So the first thing is a pinout diagram. And a pinout diagram kind of looks like this. So this right here is basically a pinout diagram for the register. You've got a box, and you've got all the pins, and all the pins are labeled. A pinout diagram is usually a little more descriptive, so you'd have more text there than like R0, R1, R2, R3. You'd probably say, read output 1, read output 2, read output 3, that sort of thing. But that's basically a pinout. So you can actually use your logically file to do the pinout. That's one right there. Specify all inputs and outputs for your whole microprocessor. So it's going to be a little bit bigger than the one I just showed you. The other thing I want you to do is include a complete block diagram with every single integrated circuit component, like big component. So basically, here I've given you a really simplified version, CM registers. But there's 4 of those. So in your block diagram, you need to have 1 block, 2 block, 3 block, 4 block for each of those registers. How big is the bus? How many CPU registers? ALU? How many data memory registers? All the control ICs. So a full block diagram. And you don't have to have lines for every bit, but you have to have lines for every connection. So for instance, each code memory register connects to the data bus, so just one line is fine for each of those. But that's the next thing in this block diagram. And then C is straight out of lab 2. I just want a list of the ALU functions and the truth table, so what select inputs choose which function. And then the last one, which is mostly just for fun, is a specification table. And I want you to compare your microprocessor that you've constructed to 2 other microprocessors that are already existing. So one is from, I'm going to pick the year and be wrong, Atmega 328. It's probably like the last 10, 15 years. And then the Apollo guidance computer from the 60s, I think. Let's just see. Apollo guidance computer. Thank you, Wikipedia. Oh, 66. I was right. So there you go. I want you to compare 3 computers. Yours, the Apollo guidance computer, and then the Atmega 328, which is the one used on the Arduino platform that we're going to use in the rest of the course. And I want you to compare some specific things about each of those things, just for comparison's sake, to see the difference. So remember, the Apollo guidance computer is the one that went to the moon in the 60s. AVR is what we're going to use in the rest of the course, and then yours. So I want you to compare total memory. How many bits can it store? How many functions can it do? How fast is its clock? How much does it weigh? And how much power does it consume? So just give me a table, 3 columns, comparing each computer, and it should be a little bit of fun anyway to see the difference between a computer from the 60s, the last 10 years or so, and then this one that we've built in the course. So that's the reporting requirements. So tuck that away somewhere, and now we're going to come back to logically and what the heck is going on with all this action. So basically what I want you to do is start with lab 3 and then add stuff from there. So let me just bring me over. Here we go. So this is this is lab 3. Here we go. There it is. So your lab 3 should look something like this. It's kind of messy. I didn't really clean it up, but anyway, that's it. So we've got 2 registers on the top. We've got 1 register in the middle. We've got 2 registers in the bottom. So the very first thing we know is that we have 2 more registers. So on the top. So that's those. And then we also know we have 2 more registers on the bottom. So boom, let's just add those in. There you go. And then we also know we have a second CPU register in the middle. And then we know that we have an ALU. Oh, I do have it handy. So there, we have an ALU down here. That right there is the big components, anyway, of our project, right? We have 4 registers on the top, 2 in the middle, 4 on the bottom, and an ALU in between. So now what we need to do is make some interconnections. So let's do the simple ones kind of first. Remember back to your ALU. Your ALU takes two 4-bit inputs. It takes A0 through 3 and B0 through 3. You've got 4 registers up here, so one of them is probably A, one of them is probably B. Let's make this one A. So let's go R0, R1, R2, R3. Boom, that's those 4, which means we're going to remove these connections. They're going to go away. And then let's make this one B. So there's one set of connections. Done. Super easy. And then our ALU has 4 outputs, and we have 4 demuxes. That makes sense, right? Each demux is going to handle 1 bit. It's going to be our 0-bit demux. It's going to be our 1-bit demux. It's going to be our 2-bit demux. And that's going to be our 3-bit demux. That's pretty easy. So then we also need to add some more inputs, right, and outputs for this thing. The ALU needs 3 control inputs, right, to choose the functions. We're going to drop in 3 switches for that. And they're going to connect, over here. And then we need outputs for overflow. So we drop those in, right? Connect all those up. Away we go. So then let's come to the top. We have, it logically freezes and crashes. Well, I can still talk about it because we can see most of it. So I've got a 4-bit register right here. That's my first CPU register. And there we go. And I've got 4 buses, 1, 2, 3, 4. And those buses are feeding this register. Right, so I've got my 0-bit bus, my 1-bit bus, my 2-bit bus, my 3-bit bus. So that makes sense, right? Each of those handle 1 bit from up above and pass it down to this register. So the first thing we need to recognize is, okay, well, that's good, right? We've got these little buses, they go to this register, that's fine. But now I have a second register that also needs to be able to get data. And we don't want these 2 registers to be grabbing the same data all of the time. We want them to be different. So what that means is that this register needs a bus structure, so it can pick from any of these registers up here. This register then needs a totally different bus structure, so it can pick from the registers as well. So what that means is we're just going to squish this in a little bit here. Compress all that. And then we just need another one. So we're going to grab all this, we're going to dump it back on, and we're going to have a whole nother bus structure over here where this one goes to this register. And then all the connections at the top are just basically duplicated, right? We got to grab all the data. So these ones are going to go, over here, R3, R3, R2, R2, and so on. This is just back to lab 3. It's just the same pattern, just bigger. The other thing we got to recognize is, well, if I want these to be able to select different data sources, right, this one needs to be able to pick something different than this one does, then I actually need a different decoder. It's called minus selector, but it's the same thing. I need a duplicate of this structure. So I actually need to stick this over here so I can separately control what this register chooses. So I got a separate decoder over here, so that this guy can choose different data than the one on the left. So you're going to interconnect this decoder with this whole bus structure. So you see how everything's getting bigger, right? We've got double the bus structure because we've literally doubled the width. So here's the other way it gets bigger. In lab 3, we were only funneling 2 registers down to 1. Now we're funneling 4 registers down to 1. So that means that our bus structure can't be 2 wide anymore. It actually needs to be 4. So we just make it bigger. I'm just going to do these with one set. I won't do both. So these become 4-bit registers. 3, 4. So then I grab not just from these 2, but I also grab from these other 2, right? All 4 registers funnel into the bus. Logically, it would stop freaking out here. There we go, R3. So this is going to be our 3-bit bus. It's going to grab this R3. It's also going to grab this R3. Right now, it's going to grab also this R2. And key that you connect these in a consistent pattern so that the mapping makes sense. This is going to grab also this R2. So all the 3s go here, all the 2s, all the 1s, all the 0s. So that means something else as well. Now, if I look at my selector, this selector isn't big enough. This selector only chooses between one of two things. It can only choose between like this tri-state and this tri-state. But now, on every single bus, I need 2 more tri-states. So this selector isn't big enough. You actually have to build a larger one. Do I have it here? 1 to 2. There we go, 1 to 4. So you're going to have to build a larger one of these. It's called a 4-bit selector. And you can just Google that if you want. This is a really common circuit. But remember, this was the logic for the single selector. The 4-bit selector looks like this. And again, just look it up. It's pretty common, simple circuit. But this thing allows you to choose between 1, 2, 3, 4 options. So now, if I just remove these connections from these tri-states, I can enable either this tri-state, or this tri-state, or this tri-state, or this tri-state to go through to my bus. Okay? So 4-bit bus, you need a bigger selector. That selector needs 2 inputs. So see everything getting bigger? This gets more complicated in one more way. So let's just go to the bottom. One of the things we also said is that we're going to be able to take this data and actually pass it back around into the CPU again. So we have a circular data path. So that means that these registers have to be able to funnel through these bus structures. So not only do we need double the bus structure because we have 2 registers in the middle, not only do the buses get twice as big because we have 4 registers in the top, they actually get twice as big again because we also need to grab data from the registers on the bottom. So not only does this 3-bit register, I even lost the label, there we go. Not only does this 3-bit bus grab the 3 bits from up here, it also needs to grab the 3 bits from the bottom. So we're going to circle right back around. You can see how this gets a little bit tangly. So it's going to grab that 3-bit. Oh, missed it. It's going to grab this one. It's going to grab this one. And a really quick way to do this, if you don't like dragging these that far, is just to pull the bus down here for a sec. Make your connections real quick. And then just fire that back up there. Okay. So this bus now grabs 3 bits from the entire system. It grabs the ones from the top and the ones from the bottom. So it's an 8-bit bus. And there are 8 of them. So we went from 4 2-bit buses to 8 8-bit buses. So way bigger. And then that again means my selector is actually too small. So you need to build a, I don't even know if I have it in this one. I'll show you it in a second. You need a 3 input, 8 output selector. So this one's not even big enough. We have a similar sort of challenge down at the bottom here where we had a 2-bit demultiplexer because it was sending to one of 2 locations, but now we're sending from our ALU to one of 4 locations. So we actually need to replace all of these 2-bit demuxes with 4-bit demuxes because each demux is going to take in a bit. So let's say this is the 3-bit demux, and it's going to pass that 3-bit to, let's just rotate it, it's going to pass it to, you know, that one. Oh, I got to delete them all. It's going to pass it to, you know, this one, or it's going to pass it to this one, or to the 3rd one, or to the 4th one. So it gets bigger. So then that's the gist of it. And then the controls also are going to get larger. This was the right control demux. You can go back to lab 3 to double check what that's all about. But again, it's not choosing between 2 registers to write to now. It's choosing between 4 registers to write to. So that also gets bigger. And then you'll end up with more controls over here. You've got these ALU controls. You're going to have more than one register destination control, right? We're choosing between 4 things. We need 2 of those now. And that sort of idea. Same with your source select. You're going to have, I think, 2 sets of 3 switches to choose your source locations because each CPU register can choose a different source and choose from 8, so it needs 3 selects. So that one needs 3 selects. This one needs 3 selects. So it just gets bigger. So all that to say, it's a larger system, but it's based on Lab 3, right? Like I just dropped in all the components. It did, I don't know, probably 20% of the connections in like 15 minutes. So you can figure it out without too much challenge anyway based on this general structure. So let me just show you how it works when you're done. So this is a finished version. See how pretty that is? So I want to show you a couple of things here. One thing I want to show you is labeling. Another thing I want to show you is function. So let me just, zoom in. A couple of tips and some circuits. This is a three input, 8 output selector circuit. Again, just look it up. It's easier than looking at my mess here. But that it looks like that. It's just both lit AND gates. This I think is a 2 to 4 demux. They're both the same. And this is just a great recommendation. Rather than having this mess of a bus thing, so it's going to be, if you do them all out individually, it's going to be 64 tri-states wide. Just make an integrated circuit out of the bus structure. So build one and then make it an integrated circuit. And I think it's here, selector, 8-bit bus. It'll look like this as a bus structure. So a little cleaner to look at. And then when you're done, you're going to have 8 of these bus things going on. And they don't have to look exactly like that. You can switch the input locations. You can do whatever you want, but that's what mine looks like. So it's a little cleaner like this than having 64 tri-states across. So that's the build. Then the other thing I want you to do, remember I said about truth tables? This is what I meant by truth tables. So I've got all my inputs over here kind of together on one side, and I've put truth tables over them just so I know what the functionality of the switches is. So this is my ALU function select, and I've said S2, S1, S0. So for instance, if I go like this, it's 1, 0, 0, which is right there. That's add, 1, 0, 0. And I can look at it really easily because the table's there. That's helpful. I've also got my A select and my B select. Remember, I've got 2 CPU registers, so each of them choose differently. And again, the switch positions that correspond to what I'm choosing. So if I do 0, 1, 0, that chooses CM2, which is code memory 2. And then if I did, there it goes, if I did 1, 0, 1, that would be DM1. And then what I should have are labels on all of my registers. Let's see if I have them. Oh, good. I have one. Labels on all my registers that indicate which one I'm actually choosing. So CM0, this would be CM1, CM2, CM3. And then you should have, I probably don't, you should have the same thing on the bottom. Let's just put one in. That indicates to you what these register names actually are. And the same thing here. This one's A, this one's B, for instance. And you want to label all those guys. And then the other thing I've labeled is what the ICs are. So this is A select, B select, I think that's data memory write select, actually. And then I've also labeled my buses, because remember, data flows in specific ways. So I have data bus, where the bits are actually moving, the information. I have address bus, which chooses where things are coming from or where they're going. And then I also have control bus, which chooses when things happen, whose turn it is, when a read or write goes, and read and write, all those things are control. So that's the build when you're done. And then if you want, you can actually use logically to build your pin out. So that right there is a really, really nasty integrated circuit. But this inside this thing is everything I just showed you. Oh, now it's going to get really mad because I clicked on it. This might take a sec. There it goes. Oh, there it is. All right. So that right there is the circuit I just showed you. Right? It's even got the labels and everything in it. So there's an integrated circuit. So the last thing I want to just show you is how to test this thing, because this is crucial in your ability to build a report and troubleshoot. So the very first thing we're going to do is load data at the top. So let's just pick some patterns. It's helpful to pick different data so you know if it's working or not, because you didn't just load everything the same. And then same as lab 3, you're going to say, okay, ready to write to those registers. And then you trigger the clock, and that then loads all that data. So we can actually turn these off if we want. It won't change anything now. And we can turn off this write command. So now the write command is off, because remember, in a computer the clock is always cycling. With the write command off, that clock can cycle and nothing will happen. Then what we do is we say, okay, we need to load these registers down here with data from up top. So we come over to our controls. And we say, okay, I want to load register A 010, so that's CM2, and I want to load register B with 001, so that's CM1. So I say, okay, I'm ready to read from the code memory, and I'm ready to write to the CPU memory, and I hit, let's just move over so we can see it, and I hit the clock, and it grabs that data. So if I look at the ones I grabbed, this one came from here, so that's CM1. This one came from there, so that's CM2, which is what we chose if we look back at our table. So those ones are loaded. Now these have memory in them, and now we're going to pass those bits into the ALU. Remember, the ALU does math and other stuff. So let's do an AND function. with those two data points. So an AND is 0, 0, 1. So I'm going to pick that function. And then I'm going to say, okay, read from the CPU memory and write to the data memory. So we're going to pull data from these guys. It's going to run through the ALU, and the result is going to get stored down here somewhere. We also need to choose where down there it's going to go. So we have a destination select. Let's just do 1, 0, for instance. It's going to pick number 2. So I think it's going to go here probably. So when I hit clock, it's going to take these two sets of bits, run them through the ALU, through the demuxes into that register. So when I hit the clock, it takes, oh, I think my select must be backwards. Anyway, it selects, yeah, I bet I'm 0 on the right. It selects the result, which is 0, 0, 1, 0, right, because it's an AND function, and fires it in there. Then we're done at the bottom. Now the cool thing is, because of the way we've built our complex bus structure, I can actually take this data and I can pass it all the way back around. So what did I say that was? DM2. So now at my input to the CPU, I can pick DM2, which I think should be that. And we can just use 0, 0, that's fine. So now what I'm looking for is this bit pattern should show up in, I don't even know what I did on B, should show up right there. So if I say, okay, read from data memory and code memory and write to the CPU memory, then when I hit the clock again, it's going to load this one from here, because I did 0, 0, 0, 0, and it's going to load this one from down here. So this data passed all the way back around, and I can repeat then a new function with my microprocessor using data I already processed. So really what's happening here is it's like we're moving down lines of code, right? We executed one line, got a result from it, and then move that down to the next line, use that result to do something else, and you can keep going and going and going and going. You can work through various functions. So that's the test. That right there was 2 complete operations based on a complete microprocessor structure. So that's the build. That's how you test it. Again, key with this thing is testing and ensuring all of the components are correct before you build the whole project. So if you build the project and your register is wrong, you're toast, because to rebuild the register, you've got to delete all these, you've got to drop in new ones. It's just a pain. So test every component individually first. Make sure that they're working before you build your project. 9 times out of 10, the emails I've gotten so far in the last 3 weeks, it's been because an elementary component, a small component wasn't working, that the bigger thing wasn't working. So always check, starting with the most basic ones. And then the only new things you need to build are the big bus. So I'd build this as an integrated circuit. You need a demux that's bigger, and you need a decoder that's bigger, and you can just find those online. They're pretty simple, and they're pretty basic circuits. You can grab those from anywhere. They're all the same. And that's really it. So that's it for the project demo. I thought I was going to have to do something on the iPad, but I don't think I will. I think we pretty much covered it pretty well, just doing the drag and drop in this Lab 3 thing here. It's pretty much what I would have done on the iPad. So that'll be it as far as project introduction goes. So make sure you devote enough time to this. It is a fairly big project. If you run into trouble, it takes a lot of time to troubleshoot. And this thing will be due in, I think it's 2 weeks, but I'll post an announcement on Blackboard that specifies exactly what the due date is. It'll be due at midnight on a Friday, same as everything else. I'm pretty sure it'll be 2 weeks from now. 2 work weeks. So this goes up on probably Saturday, so it'll be due 13 or whatever it is. Yeah, 13 days kind of from then. So that'll be it for this project, and then we'll be moving on into the second portion of the course. We actually start programming with an actual microprocessor. So that's it. As always, if you have any questions, let me know. There is a discussion forum for projects, so feel free to fire questions on there. And remember, you're all doing the same one, so you can answer one another questions probably pretty handily if you've been able to work through most of the project details yourself. You can definitely jump on there and help others and ask questions of me as well. So that's it, and I'll see you in the next set of recordings.